You guys are working on lab 3, right? Write up the reports. So make sure you come by and talk to me. I want to talk to everybody. It doesn't usually take too long, right? But it's a good thing. So make an appointment. So they're due this Friday. Okay, so this rotational motion. We've gotten involved in rotational motion. We did this previous chapter, chapter 10. That's really just the beginning. Rotational motion can be very complicated, as you will see. So now we're going to get into the second chapter on it. And we're, before we had a fixed axis, axis of rotation. Now we're going to allow that not to be fixed. And we're also going to talk about angular momentum, which is analogous to linear momentum. Now the first thing we need to talk about here is rolling. So let's imagine we have a horizontal surface and this body here, we're not specifying how the mass is distributed here, only that it's symmetrical and that we have this nice radius of curvature so it nicely rolls along, right? Example is this, like this hoop right here. Okay, and it doesn't have to be a hoop. It could be a disc, right? So it's rolling along with constant velocity here because the surface is level. And what do we mean by rolling? Well, by rolling we mean it's not slipping. And this is a key idea that you need to make sure you get here. So at any instant here, you look at a snapshot here at any instant of time. The bottom of this object here is at rest relative to the surface. There's no relative motion. If there were, we would have some, we'd have slipping. Okay, so in this moving along like this, in fact, maybe it's better now that I think about it. Let's do it over here. So this is rolling along, right? At that moment right there, the green dot has zero velocity. If it didn't have zero velocity, it would be slipping. All right? So we're mainly, almost completely, we're going to be concerned here with rolling and not slipping. And in this case, we can view the motion, the rolling motion here, as a superposition of two simpler motions. So you just add them together. That's what this is supposed to denote right here. So imagine you have a pure translation. Imagine this is just moving along like this, okay? And don't worry about the surface right now. We'll take care of that in a moment. Here's a pure translation. There's no rotation. So all the mass elements here have the same velocity, which is the velocity of the center of mass. Then here's a pure rotation, the motion we considered last chapter, a pure rotation. If we add those two things together such that omega is equal to VR, what are we going to get? When I add these, just superpose these, imagine adding these two, imagine adding this motion to this motion. What's the velocity of a point instantaneously at contact with the surface? It's going to be zero. So this is a way of achieving rolling here by adding these two motions together. And one of the reasons it's important is it only works if there's a relationship between omega and the velocity of the center of mass here. You just can't have any omega and any velocity of center of mass. There has to be a relationship. Otherwise, this point's not going to be momentarily at rest. And that relationship you can see here is V is equal to omega R. So we have this omega, we have an R here. This V has to be omega R. Only in this case will we have no slipping. So we're going to use this a lot. We're going to use this a lot. And let me tell you, from a mathematical point of view, when we're solving problems, if we don't specify we need to specify whether the body is slipping or not, or if it is slipping, the extent to which it's slipping, which gets kind of complicated. So otherwise, we're not going to be able to solve a problem. This is information we have to put into the problem, whether or not it's slipping. And typically, we're going to do the simpler case, and it's a very practical case of no slipping. So we will be using this. We've got to feed the math this, or we won't be able to solve problems. And you'll see this again and again. So we're going to take an energy approach in the beginning here. And then we'll do a dynamical approach. Later in the lecture today, we'll start to do some dynamics. But you might as well utilize energy because it actually simplifies things, as we've seen. So we now have, in addition to translational energy, we now have rotational energy. And you can see that, clearly here. We have some translational energy and some rotational energy. So there is an alternative view to this that is sometimes useful, and we will use it in one of the demonstrations tomorrow. It's extremely useful in this famous one of the demonstrations we're going to do tomorrow. It's a famous demonstration. And to be honest with you, I can't remember if we're going to use it elsewhere, but it's an equivalent way. Rather than dealing with this superposition here, you can deal with what's called the instantaneous axis of rotation. So here's the idea. Here's the motion in some instant of time, okay, and it's not slipping. So the velocity of a point on this disk, or whatever it is here, is going to be 0 here. We can view this motion over an infinitesimal time interval. Okay, it's got to be infinitesimal. You got to take the limit as delta t goes to 0. And what we see here is the object instantaneously rotating about that axis. Now you can't take a finite delta t, because otherwise this thing's going to go in. If you insist upon this axis of rotation, it's going to bury itself in the surface, right? But for over an infinitesimal time interval, we can actually view the object as rotating about this axis. So quantitatively, the kinetic energy then, oh, I'm sorry, here's I didn't point this out. From this point of view here, we have translational kinetic energy, which is 1/2 the mass times the square of the center of mass velocity. And then there's a rotational kinetic energy, 1/2 the moment of inertia about the center of mass times omega squared. Okay? Now, this other point of view, the instantaneous of axis of rotation, from that perspective, the energy is instantaneously all rotational. So it's 1/2 I omega squared, but you've got it right. You have to use the moment of inertia about the instantaneous axis. And what's the relationship between the moment of inertia about here and the moment of inertia about there? Parallel axis theorem. So here it is. Here's the parallel axis theorem. If you, I'll let you do this if you're interested. You can almost do it in your head, or maybe you can do it in your head. If you take this expression and substitute it in there, you get exactly this. Okay, so these are just two different ways of looking at the same thing. And usually we will stick to this, but this has at least one important application that we'll see tomorrow. Now we've been talking about a level surface. What happens if we have an inclined surface? And again, we're going to assume no slipping. Well, the object's going to roll down the incline. There'll be an acceleration of the center of mass, right? What's going to happen rotationally? Is it just going to slide down like that? If there were no friction, which we've assumed in this class a lot, it would just slide down like that. If you release it from rest, it'll just go down and slide. But with friction's going to cause a torque about the center of mass here due to this frictional force here. And that will cause it to angularly accelerate. And it has to angularly accelerate in this way if it's not going to slip. If this thing is, the center of mass is accelerating down here, the angular velocity has to get greater and greater because if we have no slip, which is what we're going to assume here. So the frictional force, the static frictional force, supplies the slipping. Supplies the force to make the object roll here and not slip. Now this may surprise you, but we've actually assumed this before, but I don't think it was pointed out. Because friction is involved here, you might think that you're going to lose energy. But is that true for static friction? There's no rubbing. So there's no loss of, ideally there's no loss of energy here. So mechanical energy will be conserved. Now in reality, when anything rolls along, there is, and some of you might have heard of this, when something rolls along, there's going to be some frictional forces due to various effects. And that's called rolling friction, okay? And we'll be neglecting that. It's often small, we're going to neglect it. There's one demonstration where it can't be neglected, and we'll see that today. I'll point it out to you. Okay, so let's do a problem using energy approach here. Let's just do a simple problem. We have an inclined plane, a uniform gravitational field. We release a sphere, a uniform solid sphere from rest at the top, and we want to find the velocity at the bottom. And it rolls, we're told that it rolls without slipping. So, the initial energy is what? Well, we have to set up, let's call this zero potential energy. It doesn't matter, as we've seen. The initial energy is all potential, mgh. Okay? The final energy, right at the bottom here, we're going to have translational kinetic energy and rotational kinetic energy. And there's a relationship between these two. And here it is. There's the no slipping condition. We got it. Without that, we got one equation and two unknowns. We haven't specified the system. But here's the no slipping condition. When you substitute this into here, you can see, and we substitute in the moment of inertia of a sphere, this is a uniform solid sphere. Energy conservation tells us this has to be true. And now we can solve for the velocity of the center of mass at the bottom. And there's the expression. It's the square root of 10/7 gh. Now what should we compare this to? What's the natural thing to do here? What if it's sliding without friction? We've solved that problem before, dynamically and energetically, right? What's the velocity? Remember, it's the square root of 2gh. Very simple. And you encountered that in the conservation of energy experiment a week ago, last Friday, right? I got two courses, both with labs. I get confused. Okay, so if it slides without friction, then we don't have this, okay? And if you track through the calculation, which we've done before, you're going to find that it's the square root of 2gh. So what is this relative to the square root of 2gh? Is it greater than or less than? It's not the same. What is it?
No, it's less than.
It's less than. And physically, why is it? It has to be. It's less than because it has to be. And why is it less than? From an energy point of view. We've got this initial energy. The energy is going into translational and rotational motion. If we want the thing to move the fastest at the bottom it can, what do we want to do? We don't want to lose any energy into rotational motion, because that's not helping us if we want a large translational velocity here. So the reason this is less is because some of the energy's gone into rotational motion. Okay. Now there's something else interesting about here. What happened to the mass of the sphere? What happened to the radius of the sphere? They scale out. It's independent. So, you can double the radius here. You'll find that it all cancels out. Or you can double the mass. It all cancels out. So this is a prediction. If I release different uniform solid spheres from rest at the top of an incline, which one gets to the bottom first? They all get at the same time, right? We're not going to do that. We're going to back off a little bit. Before we do that, we're going to do another demonstration first, but we'll do that shortly. So we specified a sphere here. Let's open this up to all bodies that have some radius with a symmetrical distribution of mass. Now the reason I say, I don't have the loaded disk here, Oh, you guys haven't seen that. Okay, we're going to consider objects here. Not just spheres, but anything that has a radius, a nice radius, and where the mass is distributed symmetrically about the axis. We don't want to have like a metal bolt in here. You saw the loaded leaning tower. Yeah, we also have a disk with a bolt in it. What's going to happen if I release it from rest? Just take a while. What does your intuition tell you? It's going to
have uniform motion.
Exactly. It won't be uniform acceleration. It'll speed up, slow down, depending upon where the mass is. We're not going to consider that. Okay. So conceptually, we can consider this. The mass is symmetric. I'm going to release these from rest. Which one gets to the bottom first, or do they both get to the bottom at the same time? Now, this is a particularly simple case. They both have the same radius, they both have the same mass. So we've removed that, even though it doesn't matter, we've removed that. We're going to focus just on the mass distribution here. Okay, so who thinks, what do you guys think?
The one close to you will get there first.
Okay, how many people think this one's going to get there first? How many people think this one's going to get there first? Wow. And how many people think they're going to get there at the same time? Okay, we're spread out here. We got a nice distribution. That's what that's called, a nice distribution. Look, the mass is more concentrated at the center here. If I can imagine all the mass here concentrated to a point, and all this is massless, and you know this is pretty light, okay? What's going to happen? What if I have a body rolling and all the mass is concentrated at the center? What's the rotational kinetic energy going to be? It's got very small. It's got very little moment of inertia because it's so small. So this doesn't eat up as much rotational kinetic energy as this. It should get to the bottom first at first. And let me do this at the same time. Very noticeable. Yeah. Now the manufacturer made this with these very heavy steel hoops like this, and I've done this in the past, and it would just sometimes this one would beat the other one because there are non-uniformities here. You know, it's not perfectly flat. I tried to level it this way, so finally I modified it, and now it's very obvious because this is so light. So the problem what they didn't see here, and it's just, you know, why would you go to the trouble of making this, you know, beautiful thing? These things slide, incidentally. This is beautiful, right? Why would you make this if this mass, the moment of inertia here, was dominating the change in moment of inertia there? That's stupid. But, you know, that's part of their business, evidently. I don't know. It's
a deal on steel hoops like this.
Okay, so that's a dramatic example of how the distribution of the mass changes. We wanted to get something's going to get to the bottom first, or equivalently be moving the fastest. If you bring the mass closer to the axis of rotation, reduce the moment of inertia. Okay, so here's the general problem here that we're just talking about. We've got kinetic energy. Omega is VCM over R, no slipping, and we can plug this in. Now we can factor out VCM, and it's convenient here to solve for the translational kinetic energy, because if we want it to get to the bottom first, we want to maximize the translational kinetic energy relative to the rotational kinetic energy. So you can follow through with this. We can put it in the following form: the percentage of the energy at any point in time here, the percentage of the energy in the translational motion, the translational kinetic energy divided by the total energy, is 1 over this 1 plus beta, this dimensionless quantity here. And here are different values of beta. For a hoop, the moment of inertia is mr squared. When you plug that in there, beta is going to be 1. Okay? There's a mistake here that I can't believe that I made. Please correct this, and I'll edit it. this should be K translational divided by K. The translational, I got these need to be flipped, and similarly here. Now the rotational kinetic energy has to be just 100% minus the percentage of the energy in the translational motion, because we're not losing any mechanical energy here. So here's a disk, okay? Here's a solid sphere, and here's sliding, or equivalently all the mass imagined to be concentrated at the center of mass, so there's no moment of inertia. This is an old problem that we've solved. This is where you get the square root of 2gh for the velocity at the bottom. 100% of the energy is in translational motion. It's going to get there first. And here's our rank. You can see I've ranked them here depending upon what the object is. A hoop has a mass that's out there. It's going to go slowly. Okay, the disk is going to move faster. It's got a greater percentage of its energy in translational energy, and then a solid sphere. Okay, so, and furthermore, what if I have a different hoops? What's going to get to the bottom first? The mass and the radius is not there. Okay, so all spheres should get to the bottom at the same time. Before we race these things against each other, let's confirm that they all get. Can everybody see this? Okay, there's a little steel ball here. So these are very different balls, right? See how this tells me this is not, this is an experiment that's sensitive. I have to make sure I release these all at the same time, all from rest, okay? So 1, 2, 3. Not bad, not bad. Again, you know, this is not perfect. This is not flat, this is a bookshelf. It's not flat, it's warped a little bit. And I've leveled it transversely. But it's still, and I took some time doing that. Okay, how about disks? All disks should make it to the bottom at the same time. There's the same fraction of the potential energy is going into kinetic. The potential energy here is going into kinetic energy of translation and kinetic energy of rotation. The same fraction goes into kinetic energy here for all disks. It doesn't depend upon their mass or their radius. So these should all get to the bottom at the same time. 1, 2, 3. Even better than the spheres. Okay. Oh, by the way, when we say all disks, we mean all disks. Okay? All uniform disks. So I've never done this before. I didn't realize it until yesterday. I should have realized it years ago. Okay, 1, 2, 3. Not bad. Okay. Finally, oh, hoops. Now, okay, hoops. Right? Okay, 1, 2, 3. Not so good. But when you're saying this is a moment of inertia of a hoop, you're making an assumption. What is it? It's thin, right? It's thin hoop. All the mass is the same distance. And what's important is this little change in distance here compared to there. Look at this. This is headed towards a disk, you know? So we would expect this to get to the bottom first, and I think it did. Mm-hmm. Yeah. Oh, so now for the dramatic finale, right? So let's take a disk, a hoop, and a sphere. So what should get to the bottom first? The sphere, because it's got more of its mass. Let's put these in order. Maybe it's better. Let's get this. Oh, this is trouble. Okay, so it's not the overall mass, not the overall radius. That scales out. It's not important. It's the distribution of the mass here, the relative distribution. This has the most mass is relatively closer to the center than this, and then finally all the mass is out here, almost all the mass is at the radius. So this should hit first, second, third, right? 1, 2, 3. Yeah, not bad. Of course, you don't know how long it took me to get this to work. Okay, and again, it's just tricky here. You see these little pieces of paper? Can you guys see over here? Yeah, I had to level this. It's not as easy as it looks. It's not like it is in the movies. That's what people do physics demonstrations in movies. Okay, any questions? Oh, I got one. So all spheres should make it to the bottom at the same time, right? We have a winner. Adam. This is a racquetball. This is solid. So, you know the mass, this has mass closer to the center. So, this is going to beat this. And I'm going to add this to the table. The moment of inertia of a spherical shell, it's in the book, it's in the table in the book, and you can get it by integration. You have to integrate. It's 2/3 mr squared. I'll be adding that to the table. Okay, now let's go back to the classic loop-the-loop problem. We solved this before we neglected rotational inertia. We imagine we had what are those things called? The things that I hate. Roller coasters. They're called roller coasters, right? Roller coasters are going to have some inertia in the wheel, but you can neglect that. Could be small compared to all the passengers and the car, right? So it's probably not a bad approximation there. I don't know. But now let's look at the other limit. Let's look at a rolling ball. We found before that if it was rolling without friction, you should release it from rest 1/2 of a radius above here, and I marked it with the black tape. So it should just barely go around. I should have said this in the beginning. That's the loop-the-loop problem, is what's the height you have to release an object such that it barely goes around the loop here. So the normal force momentarily goes to 0 here. Just barely remains in contact with the loop. So, why is this not working? It's not, the rolling friction here, I want you to neglect it right now. Okay, let's neglect it. We're going to see later that it does actually come in here, but that's not important right now. Energy is going into rotational motion. So the velocity this thing has here is not going to be, if it does make it up here, it's not going to be as great as it were if it just slid without friction here. The fact that it's rolling, we're going to lose speed, which means it's going to depart early. And it does depart early. You can very, very clearly see it. Okay? Let's solve the problem of where we should release it so that it barely makes it over. That's a theoretical problem. So here's the theoretical problem. This is very similar to the classic problem we solved before, neglecting rotational inertia, way back in a previous chapter, except now we want to include rotational kinetic energy. So at the top of the loop, here's the force diagram. Now we're going to assume that the radius of the ball is small compared to the radius of the loop, which is not a bad approximation there, but you can actually solve it in general. It can be big here. And that might be a homework problem, but I don't think we're going to do it. But I'll bet well, I don't know. But let's just assume for simplicity here that this is small. Newton's second law tells us that the net force is actually the acceleration to center mass. This is going to be small, so it doesn't really matter here. But technically, we use Newton's third law for a system of particles here. It's referred to the center of mass motion. Right? Remember Newton's second law? You can imagine all the mass to be concentrated at the center of mass. And then the net force is the mass, the total mass, times the acceleration of the center of mass. So we're being careful here. And because right at the top here it's uniform circular motion, we use v squared over r as the acceleration. Again, we set the normal force equal to 0. That's the critical condition. It just barely remains in contact. Okay. And now we write down energy conservation. Well, before we do that, excuse me. To use energy conservation, we need to write down what the kinetic energy at the top of the motion is there. There's translational kinetic energy. There's rotational kinetic energy. We're assuming a uniform sphere, solid sphere. We're assuming no slipping. Omega is v squared, v over r is omega. And we get this, okay, for the kinetic energy at the top. Now we can use our previous result here. mv squared is equal to mgr. And we did a similar thing when we didn't have, when we assumed no rotational motion. We can use this to express the kinetic energy at the top like this. And now we use energy conservation. The energy at the top is the kinetic energy, which is here, plus we're going to call zero potential energy down here. It doesn't matter. We'll call this zero potential energy. So at the top there's mg times 2r, right? That's the potential energy. So this is the energy at the top. This is the initial energy. We set them equal and we solve for h. And we get 27/10 times the radius. And we can check this. Because we have rolling now, we have energy going into rotational kinetic energy. We have to release it higher, as I was describing to you. It has to be higher. So this had better be greater than the 5/2 over r, and you can see it is, right? Not by a whole lot, but if you multiply by 5 over 5, you get 25/10. And this is greater. It is greater. But just a little bit greater. Okay, it's actually right here. So let's see if it works. So here's the sliding without friction. Here's rolling, right? Without rolling, assuming no rolling friction. What do you think? Did you see it depart? Look at this again. You see it go like that? It doesn't work. The theory doesn't work. What's wrong with the theory? Yeah, that's part of it. But when an object's rolling along, the rolling friction is small here, in this case.
Because it's on two sides.
So there's two effects that occur here. It's sitting in a V, so it won't wander off, right? This is you can see this is a, right? This is a right angle aluminum. So there's two things that happen here. First of all, this thing is spinning a lot more relative to its translational motion compared to if it was just moving along, moving along here like this. Because it's sitting in this, because the axis of rotation is here, it spins a lot more. In fact, if you could somehow change the angle here and have the axis of rotation just a little bit below there, it's going to spin like crazy and hardly translate at all. There's actually a toy that utilizes that effect. So we're losing more energy into rotational energy than we're assuming when this thing when this is the surface. The other thing, and I think you'll buy this too, is because of this geometry here, there's going to be rolling friction. Okay, more so than if it was just moving on a ramp like this. And you can kind of see it here. You can kind of see this circular motion here introducing, I think. It seems reasonable to me anyway. So those two effects both mean you have to release it higher. And empirically, just experimentally, you have to release it here. fact, if you listen to it, it barely, yeah, I think it barely departs up there. This is right around the critical condition. Quite a bit more than the theory here. And of course, the manufacturers knew all of this when they don't know this. They think differently, right? Let's use some right angle aluminum and bend it. You know, it's not that easy to do, right? And make it nice and smooth like this. They have problems there. I guess, you know, the physics professor's problem is to figure out what's going on with the apparatus. Okay. Any questions so far?
How much energy is taken out by deforming the loop?
Making it elliptical or something?
Oh, the fact that the right angle has been distorted?
No, I mean that, you know, as it goes around, you can see it kind of shifts the track.
Oh, this motion. Oh.
Does it spring back?
You're on the right track. So you're absolutely right. You know, now I'm using a pretty light ball here. This is a sort of a plastic type ball. So, but you don't want to use, you know, heavier balls like this. The effect that you're describing. So this. Wait a minute. It's supposed to work, right? This one works. This one's a little bit bigger. So what's going on here? Mitch is right, we're losing some energy. Now it's going into mechanical energy. Some of that mechanical energy is being lost to friction, but it's not really going to come all back. It's gone from the relevant, what we care about, the motion of the ball. Okay? So there's two problems here. We're losing more energy into this vibrational. It's not a rigid structure, but there's something else, and you can hear it. I think there's just more friction here, okay? For some reason. I don't really know why, but there's more friction. It's making a lot of noise. And so consequently, it doesn't make it. Oh, here's one other thing we can do. This ball, it's sitting out like this. It's not sitting fully in the groove. Okay? Barely makes it around. It's not sitting in the groove. What about this ball? It's in the groove now. I don't know if you can see, but it's making contact right about here. It's fully in the groove. What's the difference going to be with this ball? What do you expect?
That's not getting circle.
Can't hear.
Yeah, we'll make the circle.
Yeah, why? We're losing.
The axis rotation is closer up towards the.
And because of more rolling friction, I think. Yep, doesn't make it.
So we assumed no slipping with that larger ball. Was there actually slipping occurring? Especially as it came back around the loop? On the way back now?
We're going to talk about that right now, but I don't think so. It sounds okay. This one at least sounds okay, right? Except you can tell it's departing there. I think you're talking about that heavier ball.
Yes, the larger the two that you put back.
It could have been, this is a good point, it could have been slipping. These are different materials. This one's going to have more static friction than this smooth, like billiard ball type thing, object here. So you could be right. You know, this is a good point, and we're going to talk about it. We assume I'm slipping because it's often a good approximation and it makes life easier. But you're not guaranteed. You're not guaranteed that. So we'll look at that in a moment. So now let's focus our attention on dynamics, okay? Energy is nice when we have initial and final states and we don't care about time. Energy is great. Energy conservation is a great tool to solve problems. But sometimes we want to dig deeper. We want to know acceleration. So then we usually use a dynamical approach. And you remember from last chapter that here's Newton's second law for rotational motion about a fixed axis. The net torque is the moment of inertia about the axis times the angular acceleration. And it's easy to remember this because it's exactly analogous to translational motion. Instead of force is equal to ma, its torque is equal to I alpha. Now, what about when we have something rolling? Now it's not a fixed axis, okay? It can be shown at the intermediate mechanics level that this still holds. We're not going to do it. But it still holds. It still holds for an axis moving parallel to itself. It also holds. So remember, we derive this for a fixed axis, and the axis has to go through the center of mass. That was also something we derived. Okay, it holds if the axis is moving parallel to itself. If the axis is changing direction, we're out of luck, and we'll talk about that towards the end of this chapter. There's another case where it holds that also can be shown at a more advanced level, and that's remember the instantaneous axis of rotation? Way back up here. So this is not the center of mass, okay? So there's an instantaneous axis of rotation here, which is moving along here. You can show that that torque is equal to I alpha, the net torque. It works about the instantaneous axis of rotation too. But again, that's beyond this course, so we'll just assume it. Okay, oops. So, let's do an example. And this will bring up this issue that, I've already forgotten, it was so long ago. Eric, who brought the issue of slipping? You know, could this ball be slipping? Who was that? Oh, sorry. Oh, Damon. Sorry, Damon. So that's good, because this is smooth, right? So we'll talk about this when we solve this problem. So here's this is a real problem you can do. You can imagine you have a little axle here attached to the body, and you wrap string around it, and you exert a constant force on this body, and it rolls along. We're not going to specify whether it's a disc or a sphere, solid or spherical shell or a hoop. It just has some moment of inertia about the center of mass, and it has some mass and some radius, and it's moving on a horizontal surface. And we want to find the typical thing you want to find here is the acceleration of the center of mass. Now we're assuming we have a rough surface, so there's going to be static frictional force here. However, if we pull on this too hard, you know what's going to happen. What's going to happen if you pull on it sufficiently hard? It's going to slip, okay? So we're going to have to confront that at the end. We understand that our results here are going to be based on the assumption of no slipping. So as long as you don't pull on this too hard, everything's going to be fine. The center of mass will accelerate. It will angularly accelerate due to this torque, due to the friction force here. All right. This is really not an easy. You have to think about this problem. We can actually write down 3 equations here among the variables. Newton's second law for the translational motion of the center of mass. The net force is the total mass times the acceleration of the center of mass. We proved that for all systems of particles. Newton's second law for a system of particles. Okay, that's fine. That's good. What about Newton's second law for rotational motion about an axis going through the center of mass here? Well, here's the force-torque diagram, whatever you want to call it. And we're going to apply Newton's second law through the axis through the center of mass here, this axis. What's the torque due to the applied force? 0. The moment arm's 0, right? The torque is 0. And this is going to exert a torque. It's going to angularly accelerate it. So we can write down that the torque, there's only one torque, is the moment of inertia about the center of mass times the angular acceleration. Now we put in rolling. We're going to make the assumption of rolling here, okay? And again, that's VCM is equal to omega r. We differentiate this with respect to time, and we find that The acceleration of the center of mass has to be alpha r. And now we have 3 equations. And how many unknowns do we have? We usually think here of F as being specified. We don't know the static frictional force. Right? What else do we not know? We don't know the acceleration of the center of mass, and we don't know alpha. So we have 3 equations and 3 unknowns. It's looking good, right? And let me point out, if we did not specify that it was rolling, or if we didn't specify something about the slipping, if it was slipping, we would have 2 equations and 3 unknowns. 1, 2, 3. Okay, but we close the system, we specify the system. In this case, we're going to assume rolling. So this looks good, and it's not difficult to solve once you get these equations. Okay. For example, we can solve for alpha, plug the expression here, divide by r, and substitute in the expression for Fs here to find the acceleration of the center of mass. So this is, at this point, it's pretty simple algebra. Here's the result for the acceleration of the center of mass. Here's the result, okay? And again, it has that F equals ma appearance, right? You can see, bring this up here, it's got the F equals ma appearance. And the inertia here, the inertia is certainly the mass, it contributes. And here's the rotational effect. This has units of mass. Moment of inertia is mass times the square of the distance. So this is the effective rotational inertia, how it affects the acceleration. We'd expect to see something like this. Incidentally, if we set the moment of inertia equal to 0, what do we get? That's an easy problem. If there's no moment of inertia here, essentially 0 frictional force will be required to keep this thing rolling. It's essentially a particle just moving along without the surface there. We have F equals ma. So this is the effect when we include the inertia, and it holds for no slipping. Now, as I said before, if you drive hard enough, if F is big enough, this will break down, okay? In fact, it's better here. Let's actually solve for the static frictional force. Once we know this, it's an easy matter to find, once we have one of the 3 unknowns, it's easy to find the other 2. For example, you can solve this for Fs. Solve this for Fs, substitute the expression that we found for the acceleration of the center of mass, and here's what you get. So, and we can simplify it. This is kind of unusual. Usually it's ICM divided by mr squared. But in this case, solving for the static frictional force, okay, sorry, something's bothering me. All right, so here's what the static frictional force has to be for if the object's not going to slip. It's got to be equal to this. But we know this has to break down. If you exert a big enough force here, you know it's going to slip, okay? When's it going to break down? We know the answer to that. When Fs is equal to the coefficient of static friction times the normal force, which is just mg here. If you drive harder than that, this is proportional to F. As you do this for higher and higher Fs, eventually you're going to exceed this, and it's going to slip. It will slip.
I have a question.
Yeah.
So when it does start slipping, there is a kinetic friction as it's slipping down? And does that also play a part in?
Once it starts to slip, boom, it's kinetic friction. So that's going to cause it to roll, right? Now, depending upon the situation, it may eventually roll without slipping. That's what happens in pool. If you hit a cue ball dead on, right, and I think we're going to talk about this later. We've already talked about it a little bit before. Hit the cue ball dead on, what happens is, on just a level surface, I might need this. On just a level surface here, just after you've hit it, there's no rotation. You've imparted no rotation to this. You just hit it dead on like this. So you have this initial velocity. In fact, can you hear it? I don't know, it's hard to hear. But right after I release this, the center of mass is moving and it's not rotating. So what's going to happen? There's going to be kinetic friction this way. It's going to angularly accelerate it, and then what eventually happens? Very quickly. No slipping. It rolls without slipping. So that's a classic example of, where you have both in the motion. And you can solve, it's possible to solve for that motion. I don't think we're going to do it in this class, but it's possible. We could do that. We know enough to solve for the motion. Now, I've forgotten your question.
No, that was it.
But that was kind of, okay, good. All right, so any other questions? So we have a lab this week, right?
Last one.
Yeah, it's a rotational